This little video is to address questions about when do you develop a model, when do you need a model. You're looking at a risk assessment that was used by the U.S. Food and Drug Administration to assess the risk of Vibrio parahemolyticus in oysters. Now let me show you this model. If you just look at the column E there, you see it goes down to about 44 rows. So when this risk assessment began, what you need early on in the process, perhaps as early as the risk profile, if not that early, soon after that, is the risk managers need to know that I would like to know how many people get sick each year from eating Vibrio parahemolyticus in oysters. They would have to know at least that much. And they might also want to know that I'm looking at several different risk mitigation measures. We're looking at a heat treatment, a freeze treatment, and a rapid cool mitigation. So maybe that's all you know early on, but the risk managers have to tell the risk assessors that this is the information I need. I want to know how many people are getting sick, how many would get sick if we used a heat treatment, how many would get sick if we used a freeze treatment, and so on. So if I'm your risk assessor, now I begin to have some sort of idea of what kind of model I'm going to need. So it's a very conceptual, mental kind of model very early on, but you need to have that idea early on, because if I am your risk assessor, this is going to point me in the direction of what kind of data I'm going to collect and how I'm going to build this model. So once you have given me that basic idea, I might begin to draw out little circles and squares on a piece of paper that say things like, well, first there's the harvest. I get the water, get the oysters from the water, and then there is the work boat. How long do the oysters stay on the work boat? And then there is storage, and then there is consumption. So my model might just have those four circles or squares: harvest and work boat and storage and consumption. And then I have to begin to think about what kinds of calculations am I going to need for this model. And that's when I begin to get to the spreadsheet. I'm going to get into the spreadsheet here, and I'm going to show you that, once we begin to identify those equations that we need, for example, how much Vibrio is in the oyster when it is harvested, and then how does that Vibrio grow. So I'm going to need a growth equation. And you're beginning to think in those terms. Now this is all happening, this might be happening as early as when the hazard identification is going on, but the model kind of runs parallel to all of those steps, if you will. You begin the model as early as possible, and you're going to iterate it, refine it as you go. So it doesn't really occur, we can't really say the model occurs in this step. However, there are steps in the risk assessment that are often important inputs to the model. So for example, I'm going to show you the exposure assessment. In this model, I'll show you the exposure assessment, and then I'll also show you the hazard characterization. Here's how the exposure assessment begins. We are right here in this cell E8, and this is giving us information about the water temperature. I'm not going to go through the model in detail because it would take too long, and no one's really interested in the particulars of this model. But we're saying the first thing I need is a water temperature, because a water temperature is a primary determinant of the amount of Vibrio that's in the oyster flesh when it's harvested. And so those of you who are interested can look up here in this function line as I go through the model. I won't be explaining everything that you see, but you will see here there's an equation that basically takes the water temperature and calculates a number of log count of Vibrio per gram of oyster flesh. So what we're trying to do is we're trying to tell a story here, an exposure story. How many Vibrio is this person going to eat? And this model is for an individual person. Depending on what the risk assessors might want, I might have a population model here where I'm looking at everyone eating all at once. In this case, This green column E is just giving me one person eating one meal. So I'm basically saying, okay, when the oysters come out of the water, they have almost 2 log counts per gram of oysters. And then the oysters spend some time on the workboat. In this case, it's 6 hours. Of that 6 hours, some of that time is spent unrefrigerated. In this case, it's about 2.6 hours unrefrigerated. During those 2.6 hours, they are exposed to wind temperatures, which in this case are cooler than the water temperature. But during those 2.6 hours at this temperature, we have some outgrowth, some growth in the Vibrio. And that would be this number right here, just about 0.2 log counts per hour for a little over 2.5 hours, and that's about 0.4 log. Add that to the original 1.99, and now we're saying at the time that the oysters are finally put into refrigeration, they have 2.4 log of Vibrio per every gram of oyster flesh. It takes them 9 hours to cool down. During the time that they're cooling down, the Vibrio continue to grow, and we have an outgrowth of 0.86 grams, count per grams. That brings the oysters up to 3.3 log per gram of oyster flesh. In this particular case, these oysters remain refrigerated for 13 days. During that time, some of the Vibrio died off to 2.5 log per gram. Now what we need to know, I have the number of Vibrio that are in a gram of oyster flesh at the time of consumption. I need to know what the person consumed. This person was quite a fan of oysters and ate 529 grams of oysters. If the average pathogen load was 2.4 log count per gram, then you can see this person consumed a great deal of Vibrio. That's a log count. Now, not all of those Vibrio were pathogenic Vibrio. So to find out how many pathogenic Vibrio this person consumed, you'll notice there's another equation in here that says of all of those Vibrio, 227 were actually pathogenic. Now, if you consume 227 pathogenic Vibrio, that's the exposure. This is, everything up to here was the exposure assessment. And so this part of the model could have been built early in a crude way and refined as you go. It could have been built out conceptually, and then you would have to wait till you get the data. And that might not happen until after the exposure assessment. But this part of the model is exposure assessment. Okay, so the next thing we want to know is, okay, if I consume 227 pathogenic Vibrio, tell me what that adverse effect is. This is the hazard characterization piece. Now, what you won't necessarily have a deep understanding for is in this yellow cell. If you look up at the function line, there is basically a dose response curve, and it takes the number of pathogenic Vibrio and converts that to a probability of illness. In this case, it's 8 people out of 1 million. So if 1 million people consumed 227 pathogenic Vibrio, we would expect on average about 8 of them would get sick. Down here we have the punchline. Is this person one of those 8? And a 0 is telling us no, they're not. If there was a 1 here, that would be telling us yes, they are one of the people who get sick. Now, I understand that from what I just said, you don't have a feel for how this model works. That was not my intention with this particular video. What I'm trying to express to you is that different parts of this model, for example, this dose response curve, if you are using work that's been done by FAO and WHO, that dose response curve may be already waiting for you, on the shelf and waiting for you, where you've decided we're going to use that dose response curve. If you're going to develop your own, that's going to be a more detailed analysis, and so that won't happen until later in the hazard characterization. So the steps don't always proceed nice and linearly. We say first hazard identification, then hazard characterization, then exposure assessment, then pull it all together in a risk characterization. And sometimes it might work like that. But more often than not, you begin the hazard identification and you begin the hazard characterization and you begin the exposure assessment all at once, especially if you have different people working on the risk assessment who know they have different responsibilities. They begin all at once and they feed off of each other, and sometimes you go down a blind alley and you have to stop and turn around and come back and start over. And so the models will evolve throughout the risk assessment process. Once you do have a good model, however, and this is one of the reasons why FAO and WHO are doing some risk assessments that can be used by other people around the world. Sometimes once you have a good model, other people can adapt it and use it. So I'm not sure if this gives you a good idea or not. I'm going to ask you to come back to me and let me know if it doesn't. But let me address this while I'm here. In column G, I had mentioned earlier that we were going to look at a heat treatment, a freeze treatment, and a rapid cool mitigation. Essentially, what this is doing is it takes these oysters that we were describing in column E, and once we get to this point, the oysters all have a different fate. So this says the predicted level after die-off of oysters that are just harvested and routinely handled, they would have 2.4 log count of Vibrio per gram. But if you cooked the oysters for a 4.5 log reduction, that would go down to a -2 log count. If we freeze the oysters, which would result in a 2 log reduction, it drops down to a 0.45. And rapid cooling would reduce it from a 2.45 to a 2.0. Notice what happens. Down here, that translates into fewer pathogenic Vibrio being consumed. And that, of course, means the probability of illness is going to be even smaller. And the bottom line then, of course, would be that hopefully we would have fewer people getting sick. So I need to know these things. If I'm your risk assessor, I need to know what kinds of information you need. So we're going back to those kinds of questions that we asked in the water supply exercise. You've got to get those questions right, and then I can say, okay, I know what I need to do to answer them for you. Okay? So if you've got further questions, please ask, and we can continue this discussion in class.